Hello, I'm Burcu. I'm a postdoc at Max Planck Institute for Software Systems. In this video, I'll present a method for verifying transactional programs, whether they satisfy application invariance or not, when they are run on top of weakly consistent databases. Let's start with traditional databases and database applications. A database application consists of a number of transactions which manipulate a set of database variables. And clients can operate on these variables by issuing transactions. They can connect and issue transactions concurrently, and a correct database application should maintain database invariance in any possible execution of those transactions. In traditional database systems, asset properties are used to preserve the correctness. Asset stands for atomicity, consistency, isolation, and durability. Atomicity requires the effects of a transaction should take effect atomically. Consistency requires a transaction to affect data only in some allowed ways. And with asset guarantees, we require strong consistency, where the transactions operate on the variables as if they are run on a single copy of them. Isolation requires no interference between the execution of transactions, and durability says once a transaction is committed, its updates are persistent. These properties lead to serializability. The resulting execution of the set of concurrent transactions is equivalent to some serial execution of them. Here we see an example. This transaction operates on accounts table. It reads the balances of accounts X and Y, and if the summation of those accounts is greater than 100, then it subtracts 100 and writes it to account X. So with asset guarantees, before another transaction runs, the servers synchronize. And even if the second transaction connects to another server, it sees the effects of the earlier transactions. We say T1 is visible to T2. So the second transaction also reads accounts X and Y. And this time, if the summation is greater than 100, it writes the subtracted value to account Y. But here it does not, because the value is not greater than 100. Let's say that we have a database invariant, an application invariant, which requires the summation of these balances are non-negative. As you see, any serial execution of those transactions satisfy the requirement. Let's turn to modern systems where the servers are geographically distributed. Brewer's cap theorem states that it's impossible to get all three of strong consistency, availability to user requests, and partition tolerance, being able to operate even in case of network partitions. And modern databases sacrifice strong consistency in favor of availability and provide weaker forms of consistency. While with the strong consistency, we had high latency due to synchronization, and it wasn't the systems weren't partition tolerant. With weak consistency, we have low latency, and the system is partition tolerant. But this comes with a price. With the strong consistency and asset, we had serializable transactions, which provided an illusion of a single copy, which was easy to reason about and write the applications for it. With weak consistency, we have a larger set of allowed program behaviors. We have anomalous, non-serializable behaviors. And depending on the consistency model, the transactions can read stale data. For example, here, T2 may or may not see the effects of T1. Transactions may concurrently update the same set of variables, or for the concurrent updates, servers can see them in different orders, and so on. Here, the same example we've seen earlier, running on a weakly consistent store. So this is T1, which wrote -440 to account X. Let's say that we're running another transaction, the transaction we've seen earlier, on another server, which is unaware of the updates of T1. In this case, since X and Y will be read both as 60s, The second transaction will write -40 to account Y. And after once the servers get synchronized, the application property will not be satisfied. We have another example. In this example, the transactions try to schedule an event to a slot, a timetable slot. And a transaction reads a number of slots, finds an available slot to an event, and if it can find one, then it schedules the event for this slot. And T1 here, let's say, writes to slot I. Similar to the previous example, T2 operates on another server which does not see the effects of the first transaction. And let's say it also reads the slots, but this time schedules another event on slot J. Let's say that we have the application property saying each slot is assigned once. And if the consistency model, although it allows concurrent executions, if it disallows conflicting concurrent updates, here the requirement would be I is not equal to J, then this property is satisfied. So here, notice that the access patterns to the variables are the same. They read a set of intersecting variables, and they write to the different variables, but which are read by the other transactions. However, the first application fails to satisfy the property, while on the same consistency model, the second one does. Then we see that actually there is a need for checking application-specific properties. And in this work, we present such a method. We present a symbolic execution-based technique to verify application-level properties of transactional programs. And here we assume the correctness of the underlying weakly consistent database. Assuming the database produces the behaviors only allowed by the given consistency model, we ask whether the application satisfies its properties or not, given the anomalous execution of the model. We also provide a modular analysis, and we do this for a spectrum of consistency models, from strongest serializability to weakest causal consistency. Namely, we provide also for snapshot isolation, parallel snapshot isolation, and prefixed consistency. Here is the high-level summary of the method. We take as input a number of transactions, a set of transactions, T1 to Tn. We take the application invariance, 5 properties, and also we take from the programmer a consistency model as input, on which we will check the execution. Then we build a formula based on those inputs, and if the formula is satisfiable, we say that the application property can be violated in some executions. And if it is not satisfied, then we say that the property is satisfied in any possible execution of the transactions in the given consistency model. How do we build phi? We summarize the effects of the transactions symbolically. We connect the symbolic valuations of transactions together to build an execution. And also we eliminate the executions which are not allowed by the consistency model given. We summarize a transaction as a relation between a symbolic input and output snapshot valuations. And while doing this, we take advantage of 2 properties of transactions, atomic visibility and isolation. Since isolation says a transaction runs without any interference from the execution of other transactions, we don't need to consider any intermediate values from others. And we can just start with an input snapshot and run this transaction on this symbolic input snapshot and produce an output snapshot. And also we produce the effects, we make available the effects of the transaction from X to X prime atomically. How do we bring together those summaries? This is the formula, which is a conjunction of smaller formula, and I'll explain how to build this on an example. Let's first, for simplicity, encode an execution of transactions T1, T2, T3 for serializability. So trans is the symbolic summaries of the transactions. Arbitration is a total order relation between the transactions in the system. So some systems use arbitration, which can be implemented something like timestamps or something similar, uses this total order to resolve conflicting concurrent updates. So the transactions can run in any arbitration order. For this example, and for simplicity, we'll assume the arbitration of T1 is 1, T2 is 2, and T3 is 3. Now, with the input states, we restrict what can be read as the input snapshot valuation by a transaction. So here, for example, a TI is the effects of TI are summarized by xi and xi prime, where I is the arbitration of the transaction. So each summary is calculated on the x value that matches the arbitration of the transaction. So we have those symbolic values. Input states restrict what is the input value read by T2. And for the case of serializability, what is needed is that the input to the second transaction is actually the output of the first transaction. So we tie them together by restricting the outputs of a transaction Ti to the input of the transaction Ti plus 1. Here you see T1 is visible to T2, and similarly the effects of T2 are of course visible to T3, and hence since whatever T1 wrote was already available here, T1's effects are also visible to T3. And with the output state, we summarize the effects of the transactions up to some point in the arbitration. For example, with yi, we summarize the effects up to x1. With y1, we summarize up to x1. With y2, we summarize the transactions up to x2, and so on. And init restricts the initial value. So the initial state is the input state of the transaction with the first arbitration. And we conjunct this with the negation of the application property. So to give better idea, I'll give another example of the encoding on a weaker model. So let's say this time we're encoding snapshot isolation. Similarly, we have 3 transactions, and again, for simplicity, I'll assume the arbitrations correspond to the IDs of the transactions. Since this is the arbitration 1 transaction, its effects are summarized into x1 prime, and the second transaction's effects are summarized in x2 and x2 prime, and third are in x3 and x3 prime. This time, we model an execution where T2 and T3 are concurrent to each other. So for this example, T2 sees the effects of T1, so it is T1 is visible to T2. We tie the output of T1 to the input of T2. And similarly, in that execution, of course, that's not the only execution under snapshot isolation, but that's an example execution. And the output of T1 is also connected to the input of T3, and hence T3 operates on the resulting state of T1, but T2 and T3 do not see each other's effects, so they are concurrent. The output state summarizing the effects up to some point in the arbitration is, after the execution of first transaction, of course, y1 is equal to the output of the first transaction. And for the second one, the output, the state after synchronization of the first 2 transactions in the arbitration is equal to the output of the second transaction. And since 2 and 3 are concurrent, the state, the output, the state after synchronizing first 3 transactions merge the updates of T2 and T3. If we're considering last writer wins policy for conflict resolution, then the conflicting updates by T2 and T3 will be resolved by overwriting whatever was written by T2 with whatever is written by T3. So this is by bringing together these symbolic valuations in different ways, then we can simulate different possible executions of the transactions. So this is, in the snapshot isolation, we have an additional requirement of not writing to the same set of variables by the concurrent transactions. So we also need to disallow conflicting concurrent updates. For this, we have additional restrictions on the resulting executions. So this was the formula which allowed us to tie together symbolic snapshots in some arbitrary ways. Now we'll restrict what can be the input states of the transactions and what can be the output states of the transactions, what can they write, by adding two additional formula. And for different consistency models, we allow different set of anomalous behaviors, and hence this phi read and phi write varies for these models. Prefix requires if the input snapshot of T has the updates of some transaction S, then it also sees all arbitration predecessors of S. Total viz requires the visibility of transactions to be totally ordered, which actually ensures serializability. And no conflict restricts the executions in a way that the concurrent transactions do not update the same set of variables. We show the applicability of our approach on a set of benchmarks. We implemented the transactions in Boogie intermediate verification language and instrumented them with the encoding of our formula phi. Then we use symbolic execution tool. And here are the benchmarks together with the number of transactions. And for each consistency model, whether the application properties are satisfied or not. I also list the number of queries that are generated for computing different paths of the symbolic execution to give an idea about the size of the benchmarks and the symbolic execution. This number of queries depends on the number of transactions, number of variables in the transactions, and the access patterns of the transactions, whether they read or write some intersecting set of variables, and of course, on the consistency model. Here, what I would like to show is for some applications, for some benchmarks, some consistency models weaker than serializability are enough to provide the application properties. For example, for the auction benchmark, we have two different versions implemented and verified. For given 4 transactions for opening an auction, closing an auction, and 2 concurrent bids, with an application invariant saying that whenever an auction is closed, the highest bid is the winner. In the first implementation, serializability is required to provide this property. But it is possible that some implementations, some designs of the applications, even causal consistency is enough to guarantee that the application provides this property. And similarly, in Fusion Ticket, again, the application properties can pass in weaker consistency models. And the good part of this approach is that it is parametric with respect to the consistency model, and the programmer can check which level is required for his properties to be satisfied. There are a lot of work on weakly consistent systems, but here I focus on the correctness of weakly consistent programs. And the most related work for checking correctness of programs is related to checking serializability or robustness. A program is robust if all program behaviors are serializable, even if they are executed on a weaker consistency model. Then it will be equivalent to some serial execution, and it will behave as expected. This is a generic correctness criteria. However, it is restrictive. As we've seen earlier, there were some applications which may not be serializable. And here we see the dependency graph of the example we've seen earlier. It is not serializable. It's not robust against snapshot isolation, but it is correct. I'd like to conclude with the high-level summary of our approach. Thank you for listening. I would prefer if it was in person, but I'll be happy to get your comments and questions by email as well. Thanks once again.